Hello everyone and welcome to today's lesson on velocity vectors. So in last day's lesson we were just revising the technique for combining displacement vectors, and in some of those examples it was two displacement vectors at right angles to each other. Now the difference when we come to combining or adding velocity vectors together is that with your displacement vectors one follows on from the other. So when you're drawing the vectors out, for example, if you had someone walking 3 kilometres to the east, and then they walk 4 kilometres to the south, then the two vectors that we've drawn out, one follows on from the other. Okay, so there's your start position there, and as the person walks out that displacement, the next displacement vector then follows on from that. However, when you're combining force vectors, or in this example that we're looking at today, velocity vectors, both the vectors actually act simultaneously. So they act at the same time on the object or person in this case. So in the example that we're looking at, the velocity vectors, there are two of them, they're acting at the same time, right, as on the swimmer, and when we're drawing out these vectors they should be drawn out so that they are head to tail, okay, just like we did with our displacement vectors. But when you're looking at the scenario here from this example, so the swimmer is swimming across the river, or aiming to swim across the river with a swimming velocity of 1.5 meters per second, but at the same time the river's pulling him downstream, as shown on the diagram here, and the river is moving, or the water in the river is moving at 3 meters per second. So basically what happens is, although the swimmer is, here's a wee swimmer here, just trying to swim across the river, the river's pulling him downstream at the same time, so we end up with him sort of drifting somewhere in this direction here. Okay, so that would be the kind of direction you'd be expecting for your resultant velocity. That would be what someone else would observe if they were on the shore here watching the swimmer come across. So they wouldn't be coming straight across, but instead sort of drifting along with the flow of the river. So we would say that those two velocity vectors here and here are acting on the swimmer at the same time. Okay, so what we then have to do is to redraw the vector diagram so that you have these two vectors arranged head to tail. Okay, and we're just going to have a look at how we would draw that out. Alright, so let's have a look at the solution to this problem then. In the original diagram, one of the things that I'd forgotten to show is that we have the north direction, so that'll help us with our bearing when we come to work out the direction. So as we've said above, that we need to redraw the vector diagram so that the two vectors are drawn head to tail. So in this case I've chosen to draw the swimmer's velocity vector first, and then on to the end of that I've drawn the velocity vector for the pull of the river as it pulls him downstream. Okay, so the 1.5 meters per second vector there, and then on to the end of it there you've got your river velocity of 3 meters per second. So head to tail just means that the head of the first vector is on the tail of the second vector. Okay, where the arrowhead obviously represents the head or front of the vector, and the other end represents the tail of the vector. You could have chosen to draw the green first and then the yellow onto the end of that one, and the solution would end up the same. Okay, so you can try it that way as well. So once we've drawn this out, we can see that we've got a right angled triangle. Okay, so that means that we can use Pythagoras to work out the size of the velocity vector. We'll just draw in the resultant velocity first, and we'll just use the double-headed arrow just to show that that's our resultant. It's still important to mark in your start point, even though it's not a displacement. We still had a point where we started our drawing, which was here, and then we had a point where we finished our drawing once we'd drawn the two vectors out. So you still have your start and your finish point, and now we just need to go ahead and use Pythagoras to work out the size of that velocity vector there. Okay, so we'll just mark in that that's the resultant velocity. So you can see the first part of the solution there now. So we've just used Pythagoras to work out the hypotenuse of the right angle triangle that's there. And so that's us solved the magnitude of this velocity, but of course velocity is a vector quantity, and so we need to find the direction as well. So when I said at the start there that you were, when we're drawing out the diagram, that we had a start of our drawing, that's where I want you to mark in the angle. We'll call that angle theta. So in the next part of the solution, we're just going to see how we can use trigonometry to work out the size of the angle theta. Okay. So using the tan function there, tan is equal to opposite over adjacent, so that's 3 being the opposite of where you had your, that's why it's important to get the right angle here. So the opposite is here, adjacent is here, so it's 3 over 1.5, which gives us 2, and then we find theta from the inverse shift tan function, which gives us 63 degrees. Okay, but we're not quite finished yet because we need to work this out as a 3-figure bearing. So if we go back up to the original diagram, remember that this direction is north, so that means that we can mark that in on our drawing here. So that direction there is north. So the angle that we're actually trying to work out, so that we've got a bearing, is the angle clockwise from north until we get to the direction of the resultant velocity. So it's this angle here. Okay, so we know that to go to there is 90 degrees. So we just need to then add 63 onto that to give us the 3-figure bearing. Okay, so that's an angle of 153. Okay, so the final solution then tells us that the velocity vector that we've been trying to work out here is 3.35 meters per second. And our 3-figure bearing is 153 degrees. Okay, so it's the same method that we used for combining displacement vectors. You might have done a bit of this at National 5 as well with velocity vectors or maybe even force vectors, but the kind of key step at the beginning is to redraw the vector diagram so that the two arrows for the vectors are head to tail. Okay, and then from there it's just the same technique as before. Okay folks, so just going back to the booklet that you were working from yesterday, booklet 1A, and this example, this worked example, is on page 11 of your booklet. So this is actually just taking it back to just a one-dimensional example, similar to the one that we looked at with the swimmer there. We've got a boat which is moving, travelling upstream in the river. Okay, so the river's flowing this way to the left, and the boat is trying to go upstream. So you've got a maximum velocity for the boat, which is 25 meters per second, but at the same time the river's obviously flowing in the opposite direction at 7 meters per second. Okay, the boat is trying to go upstream in the river. So because it's one-dimensional, it just becomes a lot simpler. All we're really doing is we're combining the two vectors together. You can look at it as though we're just subtracting 7 meters per second from 25. Okay, that gives you 18 meters per second upstream, or you can actually draw it out in full as a vector drawing, as we can see here. So you use the arrow for the boat's velocity, 25 meters per second, and then onto the end of that, remember we draw them so that they're head to tail, so you then draw the other one onto the end of the first one, So the 7 meters per second river velocity takes us to here, and that means that from start to finish we'll have a velocity vector of 18 meters per second to the right, in this case, or upstream, as we can see there. Just to mention, just another way of looking at this is that, remember we talked about velocity vectors being either positive or negative. So you can look at the boat's velocity vector as being positive or plus 25 meters per second. You can look at the river velocity as being minus 7 meters per second. Okay, because remember we said that if you've got two vectors which are in opposite directions, sometimes it's useful to treat one direction as being positive and one direction as being negative. And then in that sense, you're always combining the vectors by adding them. So you would do 25 plus minus 7, which is the same as subtracting 7. So that would still give you, in your solution there. So we'd have 25 plus minus 7, which gives us 18 meters per second, but the direction is to the right or upstream. Okay, it's just a slightly different way of looking at it. Okay guys, so following on from that, there's another worked example similar to the one with the swimmer. So it's again two velocity vectors at right angles, so you can have a look at the solution to that. Let me know if you get any problems with following that, but it's basically the same as what we did before. The only thing is they mention again they're going to do it as a scale drawing, which you wouldn't choose to do, I don't think, if you were able to use, because they're right angled again, you can use Pythagoras and trigonometry to work out the magnitude and direction of the velocity for the plane, okay, which is in this direction here. So see how you got on with that. The tutorial questions for this section are on page 13, and there are 7 questions. The last one is a wee bit of a toughie, so let me know how you got on with that. There are solutions to the tutorial questions, and we'll get those added to your Schoology course. Okay, guys, as usual, any questions, just send me a message on Schoology. Let me know if there's any of the questions that you want me to go through a wee worked solution to, and I can upload a video of that. Okay, but you can just message me on Schoology if you've got any questions.